So now we're back at the inhibitors. We fully try to understand the competitive and uncompetitive inhibitors. So now if we just ignore the bottom half of the table, we should be able to answer these, right? So where does the competitive inhibitor bind? To the active side. How about the uncompetitive inhibitor? It binds to the enzyme substrate complex. And now, what effect does the competitive inhibitor have on the Km and the Vmax? So on the Km, the competitive inhibitor, because the competitive, we should look at it like this. Because the competitive inhibitor binds to the active side of the enzyme, it means that it will have no effect on the Vmax in the first place, because the enzymes come back as empty enzymes. And also, when you increase the substrate concentration, you can overcome the competitive inhibitors. So it will have no effect on the Vmax. However, because the competitive inhibitors attached to the active side, the affinity of the enzyme becomes less for the substrate. So the Km increases. Therefore, you need more substrate concentration in order to overcome the reaction, and therefore the Km has increased. Remember that substrate concentration needed for the enzyme, if it's increased, then your Km is also increased. But with enzyme and substrate affinity, that interplay, it has a reverse relationship with the Km. So that's for the competitive inhibition. Also, does it bind allosterically? Hell no. It directly binds on the active side. And can added substrate overcome the inhibition? Yes. So there we go for our competitive inhibition. Now for uncompetitive inhibition, we know that it binds to the enzyme substrate complex. By binding to the enzyme substrate complex, there are less free enzymes available for the substrates. So that actually affects on the Vmax, and it reduces the Vmax. So some of those enzymes coming back for the substrates, they're full, and they have a fundamental change in their conformation, which destabilizes them or makes them more stabilized. Therefore, the Vmax decreases. Also, you need that means that the substrates, that also means that those substrates go bind on the enzyme, and then the enzyme substrate complex is affected, which means that you need less substrates to you need less substrates to to bind to the enzymes, right? Because those substrates are already binding to the enzyme, and that means that the Km is lower, so it's reduced, and it means that the affinity of the substrates for the enzymes it's higher, right? Because those substrates want to quickly jump on the enzymes. And does it bind allosterically? Yes, this is allosteric inhibition. And however, it is not on the allosteric side. This might be somewhere that I was saying that the documents might be different. So we should ask is on competitive inhibition and allosteric binding? Yes, uncompetitive inhibition is often considered a type of allosteric binding because it involves the binding of an inhibitor to a site on the enzyme that is distinct from the active site. This binding typically occurs only after the enzyme has formed the enzyme substrate complex. So, yes. Now, we know that both Km and Vmax are reduced in uncompetitive inhibition. Therefore, the binding is also allosterically. And can added substrate overcome inhibition? No, because the substrate's already attached to the enzyme, and then the enzyme substrate complex is affected by the uncompetitive inhibitor. Okay, and now here comes the last one, the non-competitive inhibitor. Let's see how the process works for this. Let's bring this up. So the non-competitive inhibitor binds at the allosteric site. So it completely binds on a different side, not close to the substrate or the enzyme, away from the active side. It does not prevent the substrate from binding to the active side. So it is not preventing the substrate from binding to the active side. Same as the uncompetitive inhibitor, right? Now, does this mean that when the non-competitive inhibitor binds to the allosteric side, does it happen after the substrate sits on the active side, or does it? So you can see here actually that the conformation, the shape of the geometric shape of the active side has changed. It is no longer a angular active side. It's now a circular active side, and that means that this conformational change, we expect it to actually have either an effect on the Km or Vmax or both. Now let's figure that out. Because that conformational change changes the active side, it means that the substrates do not sit on the active side. So no matter how many substrates you add to the enzyme, you cannot fulfill it anymore, right? And this means that when some of those substrates are going to the destination, when the enzyme comes back, the active side looks different. The car seats look different. So the substrates cannot fit into the enzyme. And therefore, that must have reduced the Vmax, right? Because you have less cars. Your cars are deforming. They're no longer available. However, the affinity of the enzyme for the substrate, does it change? Well, we need more understanding here. So let's see. How does the affinity of the enzyme for substrates change during non-competitive inhibition? Also, why is it called non-competitive? Compared to non-competitive. In non-competitive inhibition, the inhibitor can bind to either the free enzyme or the enzyme substrate complex at a site distinct from the active site. This mode of inhibition affects the enzyme's kinetics. So if it is able to bind to both the free enzyme and the enzyme substrate complex, so when it was binding to the free enzyme, it was more like the competitive inhibitor, right? It was changing, so it binds to the active site. Now here you can imagine it changing the shape of the active site of the free enzyme. So that's why the Vmax is affected. That's why the Vmax is reduced, right? Right? Or wrong? Well, when you are... So Vmax here is reduced because those active sites were changed, right? It locks the enzyme substrate complex. So the enzyme substrate complex was playing with the Vmax mostly, and this mode of inhibition affects the enzyme's kinetics differently compared to uncompetitive inhibition. In non-competitive inhibition, the inhibitor binds to an allosteric site, altering the enzyme's shape regardless of whether it's in its free form or bound to the substrate. This altered shape of the enzyme reduces its catalytic activity, but it doesn't impact the affinity of the enzyme for the substrate. The enzyme's ability to bind the substrate remains unchanged. So it doesn't impact the affinity of the enzyme for the substrate. The enzyme's ability to bind the substrate remains unchanged. The key distinction between non-competitive and uncompetitive inhibition lies in the binding site of the inhibitor. So in non-competitive, the inhibitor can bind to both the free enzyme and the enzyme substrate complex. But in uncompetitive, it only binds to the enzyme substrate complex. Non-competitive inhibitors don't compete with the substrate for binding at the active site. So they do not compete with the substrates. Instead, they exert their effect by altering the enzyme's conformation globally, reducing its catalytic activity without affecting the affinity for the substrate. So non-competitive refers to the fact that an inhibitor can bind to the enzyme whether it's free or bound to the substrate without directly competing with the substrate for the active site. I'm doing some fast work here, so bear with me. So non signifies the absence of a particular characteristic or the exclusion of something. In the context of enzyme inhibition, non-competitive means inhibitor does not compete directly with the substrate for binding at the active site. Un often denotes negation or reversal, indicating the lack of a specific quality or the opposite of something. So uncompetitive means it binds exclusively to the enzyme substrate complex, affecting the catalytic activity of that complex. Inhibitor competes directly with the substrate for binding at the active site, non-competitive. Binds exclusively to the enzyme substrate complex, uncompetitive, altering the enzyme's kinetics in distinct ways. So non-competitive means absence. The non means absence, exclusion of something, particular characteristic. Can you relate those prefix definitions to the inhibitor mechanisms for me to memorize and understand it better? Non-absence does not directly compete, binds to an allosteric site away from the active, excluding direct competition with the substrate. Un, lack of a quality, exclusively binds to the enzyme, opposite to the typical binding pattern of most inhibitors, which usually target the free enzyme or compete directly with the substrate. So reversal or opposite behavior of binding this, the on prefix highlights this reversal or opposite behavior of binding to the enzyme substrate complex instead of the free enzyme or competing substrate. So okay, for on we can say that because it is not binding to the free enzyme, it is an unusual, right? But for the non, it means absence, so exclusion, and it's not directly competing with the active site. Instead, it binds to allosteric site away from the excluding direct competition with the substrate. This absence of direct competition characterizes non-competitive inhibition. I mean, good enough, right? And oh, we forgot to ask why. So now, why does non-competitive inhibition result in reduced Vmax and no change in Km? Use an analogy with cars and passengers. Imagine transport passengers from one location to another with the speed of the car representing the enzyme's catalytic activity Vmax, the speed of the car, and the number of passengers it can carry representing the enzyme's affinity for the substrate. For us, Vmax was more like the speed of all the cars, not only one, right? So the car's maximum speed represents Vmax, the maximum rate of transporting passengers. Non-competitive reduces the efficiency of the car's engine, enzyme's catalytic activity. Even if the car is operating at maximum speed under normal conditions, the engine's efficiency decreases due to factors like a governor limiting the engine's power. So the car's maximum speed decreases. The Michaelis car's seating capacity represents km. Non-competitive doesn't affect the car's seating capacity. It remains the same. Even with the engine operating less efficiently, the number of passengers the car can carry comfortably isn't altered. So the car can still accommodate the same number of passengers as before the inhibition. The decreased maximum speed of the car due to engine inefficiency parallels the reduction in Vmax caused by non-competitive. So in non-competitive, we have still the reduced Vmax, and we need to keep in mind that Km is not changed. Another way to memorize it is that it is the opposite with competitive. So in competitive, the Vmax is not changed because you are not affecting the number of cars, right? The cars here for Vmax, we have the enzyme as car speed, like the speed of the cars or the number of cars going back and forth with empty seats. But Km is the passenger capacity of the enzyme. So the passenger capacity of the enzyme now is not changed with non-competitive because you still have all these active sites for the substrates to sit in, right? In the competitive, your spots are full, the seats are full. So that's why your Km also increases because there's more competition. But here, it doesn't matter how many substrates you add, all of them can sit, right? So it's both also what's tricky about non-competitive is that it can attach to the allosteric side on both the free enzyme or the enzyme substrate complex. So we can ask, does the non-competitive inhibitor sit on the allosteric binds the allosteric side before or after the substrate binding the active side of the enzyme. The inhibitor binds to an allosteric site on the enzyme regardless of whether the substrate has already bound to the enzyme's active site. The inhibitor's binding is not dependent on the substrate being present or bound to the enzyme. This is what distinguishes non-competitive from competitive and uncompetitive inhibition. In the competitive inhibition, the competitive inhibitor competes directly with the substrate for binding at the active site. Therefore, its binding depends on whether the substrate is already bound or not. If the substrate is present, it can outcompete the inhibitor for binding at the active site. Also for uncompetitive, it specifically binds to the ES complex, which means it can only bind after the substrate is bound to the enzyme's active site to form the ES complex. It doesn't bind to the free enzyme or the substrate alone. But in non-competitive, its binding to the allosteric site can occur regardless of whether the substrate has bound to the enzyme's active site. This strategy allows the inhibitor to exert its effect on the enzyme's activity by altering its conformation and reducing its catalytic efficiency. So that's why the catalytic efficiency, the Vmax, is affected, right? The Vmax is reduced without. So it's like again all those cars kind of going half full and coming back, kind of going fully to the destination but coming back half full to the origin, right? So some of those seats are unavailable. It's the car speed. Like you literally, the engine. I'm starting to like the engine analogy better because in normal conditions, like you're playing with the engines, right? The conformation. So wait, does this conformational change happen to the allosteric side, which then affects the Vmax of the enzyme, or does it happen to the active side, or both, or ES complex, or both? As far as we know, it's both the enzyme and the enzyme substrate complex. It typically occurs at the allosteric side, affecting enzyme's overall structure. This alteration in the enzyme structure or conformation then indirectly impacts the active site and ES complex, leading to changes in the enzyme's kinetics, particularly the Vmax. But Km is not affected because it doesn't matter how many substrates it binds to. So why doesn't it matter if the substrate is bound to the enzyme or not for the non-competitive inhibition? The inhibitor binds to an allosteric site on the enzyme in a location distinct from the active site where the substrate binds. This unique binding site allows the inhibitor to exert its effect irrespective of. So because it's on the allosteric site, has a specific binding site on the enzyme which is separate from the active site. This allosteric site might be physically distant from the active site, allowing the inhibitor to bind without directly interfering with the ES complex interaction at the active site. When it induces conformational change, conformation independently of whether the inhibitor's binding site alters the enzyme shape or dynamics globally. Because it's on the allosteric side, the conformation will change. So more specifically, this part where they bind is more like where does the conformational change happen? And for non-competitive, it is both the E enzyme and the enzyme substrate complex, right? So it doesn't rely on directly competing with the substrate for binding at the active site. Instead, it alters the enzyme structure globally through its binding at the leading to changes in enzyme activity that affect Vmax independent of the substrate present. So let's actually put this question into Google. In non-competitive inhibition, the inhibitor binds separate from the active site. The inhibitor can bind its target enzyme regardless of the presence of a bound substrate. So because we don't care if the substrate is bound to the enzyme or not, it binds to the allosteric side, and therefore it can bind to either if the substrate is on the enzyme or not. So both, it can bind to both the enzyme substrate complex and the enzyme, the free enzymes. Because it can do that, the Km is not changed. Why the whole Km concept is the substrate concentration, the affinity with the enzyme. So if you add more substrates, does it affect it? Hell no, right? So, but why it does not change is a different concept. Why does Km not change in non-competitive? Unique mode of action. Non-competitive binds to allosteric site, location is separate, includes a conformation change in the enzyme substructure, altering its overall activity without directly interfering with substrate binding at the active site. So if it's related to, let's see, Km represents the substrate concentration at which enzyme operates at half of in non-competitive inhibition, while the enzyme's catalytic efficiency decreases due to the conformational change induced by the inhibitor. The affinity of the enzyme for substrate remains unaffected because, it just, when it attaches to the free enzymes, doesn't it affect the shape before the substrate attaching? Apparently not, right? So the substrate can still bind to the enzyme's active site with the same affinity as before, as the inhibitor's binding site is distinct from the active site and doesn't hinder substrate binding directly. As the inhibitor's binding site is distinct from the active site. As the inhibitor's binding site is distinct from the active site and doesn't hinder substrate binding directly. Okay, so now we understand it. Let's add it here. Okay, I am not able to change this. Okay, here. In non-competitive, because the inhibitor binds to the allosteric side, the key here is that because uncompetitive only attached to the enzyme substrate complex, it means that both the Km and the Vmax would be reduced. But for non-competitive, because so the Vmax would be still reduced, but the Km is not going to be affected anymore because regardless, those substrates are going to sit on the active side. But so like so the cars are coming back actually as empty cars to the origin. The enzymes are coming back to the origin as empty enzymes, free enzymes. They're not going to be like half full, like the enzyme substrate complex one, right? So that is interesting. So because the inhibitor binds the allosteric side, it doesn't affect the substrates binding to the active side, nor sticking with the enzyme which was locking or getting locked up with the enzyme. why don't these substrates lock up with the enzyme like the uncompetitive inhibition? The substrates do not lock up with the enzyme in the same manner as observed. This arises from the different modes. In uncompetitive inhibition, the inhibitor specifically binds to the enzyme substrate complex, locking it into a stabilized state. This prevents the ES complex from effectively proceeding towards product formation. It traps it. In contrast, in non-competitive, the inhibitor binds to allosteric site, not directly to the enzyme. Therefore, it does not directly interfere with the substrate binding or locking up in a specific complex. Induces a conformational change in the enzyme structure globally, affecting its overall activity without specifically locking up the substrate. The binding of the inhibitor influences the enzyme's catalytic efficiency, but does not directly. What does changing enzymes conformation globally mean? Refers to altering its overall three-dimensional shape or structure throughout the entire protein molecule, not just in a localized region. The conformational change occurs globally with non-competitive, which means the whole 3D structure of the enzyme is changed, not the local region geometrical shape of the active site or the amino acid residues structures at the active site in uncompetitive inhibition. Amazing. We have fully grasped this part. Now here comes what's left, the Line-Weaver-Burk plots and the Michaelis-Menten. Let's actually watch the YouTube video on this.
Whether you're studying enzyme inhibitors for a lecture exam or a big test like the MCAT, there are a few things that you have to memorize, and I'm going to give you mnemonics for all of those in this video. The first is you've got to know what the Line-Weaver-Burk plots look like for each enzyme inhibitor. For competitive, I remember that it looks like two lightsabers crossing. For uncompetitive, the line shifts up. And so I remember uncompetitive up. For non-competitive, I think non-Km-petitive, meaning my Km does not move, so my x-intercept stays the same. Another way you can memorize it is that if you take a line and you draw it like this, and it kind of makes the graph look like a capital N. You also need to know where bind, meaning are they binding at the active site, or is the inhibitor binding allosterically like it is here? For competitive, think the inhibitor competes with the active site, so it binds at the active site. For uncompetitive, I think unocompetitive, meaning it only binds one location, and that location is the enzyme substrate complex. For non-competitive, I think no preference, meaning it binds both the enzyme and the enzyme substrate complex with equal affinity. This is it binding the enzyme, this is it binding the enzyme substrate complex. And lastly, you want to think about the effects on Km. For competitive inhibitors, I think K-competitive inhibitors, Km increases. For uncompetitive, I think under K-competitive, meaning my Km actually goes down. And for non-competitive, again, I think non-K-competitive, meaning my Km does not move. There is no change.
That's actually good. K-competitive, the Km is increasing. On K-competitive, under K-competitive, it's lower. Km decreases. And for non-competitive, non-K-competitive, the Km does not change.
I hope these mnemonics help you memorize this chart.
So this is amazing. Now we had here a few mnemonics. So first things first is the unread messages, which is uncompetitive reduced Vmax Km. And we had here also the Uno competitive. I think it was for only ES complex. Also competitive KM competitive, which is increased KM on KM competitive. It means under KM competitive, it means reduce. This is easy since we have the first mnemonic and we have non KM competitive, which means no change. No change KM. I think the other ones were for the Lineweaver
exam or a big test like the MCAT. There are, for competitive, I remember that it looks like two lightsabers crossing.
So let's get here. So we have competitive, because it's competitive, two lightsabers crossing. Which one is the upper one? The inhibitor, right? It's always the inhibitor. On competitive, it's up. So inhibitor is the upper one, right? Shifts up. Non.
For uncompetitive, the line shifts up. And so I remember uncompetitive.
Non KM competitive for last one, which is KM not changed. So SAR the same at 0, 1 over substrate.
Up for move, so my x-intercept stays the same. Another way you can memorize it is that if you take a line and you draw it like this and it kind binding at the active site, or is the inhibitor binding allosterically like it?
Also, we had here non-competitive, no preference, both E and ES. Cool. Now, boom. We are done here. Let's just go over these quickly. A double reciprocal plot of 1V versus 1S. Slope is Km over Vmax. So the slope is Y over X, which is Km over Vmax. Left side of the graph is theoretical because you can have negative substrate or velocity higher than Vmax. Vmax and Km can be more precisely calculated using Lineweaver-Burke because you are extrapolating out theoretical values. Michaelis-Menten curves show observed values only, not theoretical values. This makes calculations using Michaelis-Menten less accurate than Lineweaver-Burke. So Lineweaver-Burke is more accurate. Lineweaver-Burke allows the different types of inhibition to be visualized more clearly. Now, the whole 1 over S and 1 over V0 double reciprocal. What does a double reciprocal plot mean? And explain the Lineweaver-Burke. Is that how you write it? Lineweaver-Burke plot. A double reciprocal plot, also known as Lineweaver-Burke plot. Oh, so the whole thing is Lineweaver-Burke plot. Double reciprocal plot is these guys who created it. Is a graphical representation used to analyze enzyme kinetics by plotting the reciprocal of reaction velocity against the reciprocal of substrate concentration. Oh, so reciprocal is 1 over whatever we are measuring, right? So the Lineweaver-Burke plot provides several advantages. Linear representation, it transforms the Michaelis-Menten equation into a linear equation, making it easier to determine kinetic parameters such as Vmax and Km. By plotting the reciprocal values, it facilitates the determination of Vmax, the intercept on the y-axis, and Km, the slope and x-intercept. Through linear regression analysis. What is linear regression analysis? Explanation of the plot. X-axis, reciprocal of substrate concentration. Y-axis, reciprocal of reaction velocity. Slope Km Vmax over Vmax. The slope is equal to Km over Vmax in the linear equation, where m represents the slope. Y is the slope Km over Vmax. The y-intercept is 1 over Vmax. It's the point where the line crosses the y-axis, representing the reciprocal of maximum velocity. And minus 1 over km, it occurs at the x-axis, representing the negative reciprocal of the Michaelis. So Vmax determined from the y-intercept, 1 over Vmax. The term at km is determined from the x-intercept. The plot generates a straight line, allowing for easier determination of Vmax and km compared to a curved Michaelis-Menten plot. This plot is a valuable tool in the enzyme kinetics analysis, aiding in the determination of the kinetic parameters and providing a visual representation that simplifies the the ES interactions. I have one more question. Here we have that 1 over V equals, so this is Y. Ooh, this is good. Mx plus B. So M is Km over Vmax times 1 over S. And B is 1 over Vmax. Nice. That should also explain why V equaled Vmax times the substrate over Km plus the substrate, right? If you reverse everything here, you have V equals Vmax times substrate over Km plus Vmax. What was the V equation? What was the V equation relative to Vmax, Km, and S? So linear regression analysis is a statistical method used to find the relationship between two or more variables by fitting a linear equation to observe data points. So you want to find the relationship between two or more variables by fitting a linear equation to observe data points. It's commonly employed to determine the equation of a straight line that best fits a set of data. In enzyme kinetics, linear regression analysis is utilized to determine the best fit line that represents the relationship between the reciprocal of substrate concentration, 1 over S, and reciprocal reaction velocity, 1 over V. Regarding the slope of the Lineweaver-Burke plot, the slope of the Lineweaver-Burke plot, Km over Vmax, is obtained through linear regression analysis. It's derived from the linear equation Y. This is what you see, where M represents the slope. In the Lineweaver-Burke plot, the slope corresponds to Km over Vmax. The relationship between these equations, the Michaelis-Menten equation describes the relationship. So we had V equals Vmax times S over Km plus S. Vmax times S over Km plus S. When you manipulate it, how do you manipulate it? So start with the Michaelis-Menten equation, then take the reciprocal of both sides. So you have 1 over V, Km plus S. Then we arrange terms to isolate 1 over V. So 1 over V is on the other side. What do you mean by isolating 1 over V? It is already isolated. Km plus 1 over Vmax over Vmax times S. multiply both sides by 1 over km. Let y equal wait, so the slope is actually km over v max. Okay, so a double reciprocal plot of 1v over 1s. Left side of the graph is theoretical. V max and km can be more precisely calculated with the line Weaver-Berg. Show observed values only, not theoretical. So in competitive inhibition, we had the Vmax not changing, so we expect both lines to pass on the same y-intercept as Vmax is. And for Km, the Km was, so because it's competitive, the Km is increased, right? So we expect the minus 1 over Km if the Km is increased. Which one? So when you are increasing the denominator, the whole thing is less, right? So the one so the inhibitor, because it's increased Km, it should be a lower value. So it should be a minus 1 over Km lower value. However, because it's minus, it should be lower value. It should be higher value. It's two opposites at the same time, right? The Km increasing should make the thing smaller, but when it's minus, it's smaller and towards 0, right? Now, the Km was also reduced here. So the Km is reduced and Vmax reduced. So you expect the 1 over V and 1 over Km to go up. So the 1 over V is up, we can see, perfect. And the 1 over Km should be up, right? That means that it should be a bigger number on the minus scale. Because it's a bigger number on the minus scale, you go more to the left. Now for non-competitive, we should know that the Km, non-Km competitive, so the Km is not changed. So the 1 over Km axis on the x-axis, they both start from the same origin, but the Vmax is reduced for non-competitive. So because the Vmax is reduced, we want the bigger 1 over V line. And the slope makes sense to be Km over Vmax. How do we know that? Well, the slope is always so let's figure out what the slope is. Y equals mx plus b. So if it's y minus b, and then mx, and then it's y over minus b over x. So it's y over x. Now here, y over x is 1 over v over 1 over s. So the substrate comes up, which eventually is km, and the denominator the v goes down in the denominators, which is v max. So it's km over v max. Perfect. And the Michaelis-Menten curve is all it's a straight one, so it's v over versus the substrate concentration, and the substrate concentration is the km. So the less km you have, you for example, for uncompetitive, you expect the lowest curve. So uncompetitive gives you this lower km and lower Vmax, right? For non-competitive, you expect no change in the km. So this is your uninhibited curve, and the non-competitive should have the same km. However, the Vmax is reduced, so it doesn't go up to as the uninhibited. For Nova, you see that the Vmax is increasing. So that would mean actually that you are increasing your free enzymes. And because we're doing inhibition here, the Vmax will never increase. And that's a good point, the takeaway to have from this. And you are playing with your KMs and Vmax. So you have kind of this only scenario where your Vmax can decrease or be unchanged. So it's 2 scenarios for Vmax and 3 scenarios for KM, which is increase for competitive, decrease for the uncompetitive, and no change for the non-competitive. And this has been amazing after all. I think we fully got to understand the enzyme inhibition for the MCAT. Amazing. I'll see you till the next one, and I can't wait to do some questions on this topic. Ciao for now.